Hello, good evening, students. Okay, so it's already 7:11. So I think let's start the session. Okay, so the various people have joined, only three have joined yet. This means that most of you are actually going for holy vacations. So happy holiday to you all. Good evening once again. Okay, let's start the session. Recording. So once again, good evening everyone who joined this session and welcome you all to the live session for the NPTEL course Non-Conventional Energy Resources. This course is conducted under the banner of NPTEL and the course is taught by Professor Pratap Haridas. He is Professor in Department of Metallurgical and Materials Engineering in IIT Madras. This course is taken up by him here, Rohit. I am a PMO scholar in IIT Mumbai. So I will be conducting this live session to have an interaction component course as energy resources. So this live session has been planned as per the previous live session of the course in which we had a discussion assignment questions. We discussed various concepts. We discussed various uh, lecture material that has been uploaded weekly. So we will actually discuss these things. Apart from that, I have taken the non-graded portion of the assignment and tried to solve it to show you the concepts of the how to approach these questions and how to solve these questions. Apart from that, I have also taken ungraded graded assignments question from previous run of this course. So I will try to solve those questions in front of you and we will discuss about the have have an approach about the concept that is needed to solve this type of questions. Okay. So once again, I welcome you all. Uh, let's start this session. Okay. So the question one is the highest occupancy, highest occupied energy level in at 0 Kelvin is Fermi energy level. Is it true or so? Yeah, it's a true statement. This is about how it's true. Okay. So let me tell you about this question. So it's top this question is talking about highest energy occupied level, which is this metal, and the temperature remains at 0 Kelvin. So we'll talk about that. And Fermi energy level, this is three concept that is talking in the question. You know the energy level. Energy levels are the different levels of different levels in which the electrons are present. Okay? You must have heard about different levels in an atom. Based on these different energy levels, the electrons have some energy in it that these levels carry. Okay, so the question is asking the highest occupied energy level in 0 Kelvin. So it's talking about 0 Kelvin. So what is 0 Kelvin? So Celsius is 273 Kelvin. Okay. Then 0 Kelvin is minus 273 5 degrees Celsius. Okay. It is expected that at this temperature, all the entropy dies. Entropy of a material. Entropy is absent, no entropy is there, no entropy is there. And the metal generally behaves like a superconductor. Okay, so whatever current you pass through the metal, there is no resistance to the flow of current. So there are various properties that are at its peak at 0 Kelvin. The third thing is Fermi energy level. So Fermi energy level is the highest energy level that an electron can occupy at the absolute zero temperature. Okay, so there can be various levels, but till the highest level up to which electrons can occupy is the Fermi energy level. Okay, so if this is the level to which electrons can go, say this is the valence band, this is conduction band, this is the level up to which electrons can go from valence band to conduction band. So this is the Fermi energy level. Okay, so yeah, it's true at 0 Kelvin, some level from is Fermi level. Okay, apart from that, Fermi level denotes probability also, because electrons cannot be uh, said to be in a particular position also. So electrons are said to be travel in wave form. So always when we talk about electron and its movement, it's a probability function in which the electrons are said to be occupied a particular position at a particular instant. Okay. Also, if we see about different concepts about Fermi level, we say that the Fermi level is basically if we talk about intrinsic and extrinsic semiconductor. Okay, so intrinsic semiconductor, this valence band. Okay, if this is the Fermi level, this is the valence band, it will be very close. And be sure that at 0 Kelvin level, electrons are at very lowest energy state. In the Fermi level is actually one of the lowest energy state at 0 Kelvin, with electrons occupy. Okay. Actually, I put a thought-provoking question also here. Who discovered the Fermi level? Is a Fermi. So Fermi, Fermi, this was first. This term was first given by a scientist, an Italian physicist called Enrico Fermi, who coined this word Fermi level, and it is this level is figuring determine electrical and thermal properties of solid. So that level actually. is very important to know, especially in case of semiconductor. When we talk about semiconductor, plays an important role because the later slide we will talk about intrinsic semiconductor, extrinsic semiconductor. So these semiconductors are actually very much dependent on the where this Fermi level is actually present in between the valence and this conduction band. Okay, we'll talk about that. So join. Okay, the mic is working now. So I've changed. Is in the mic. So I think it's okay now. The question two is Fermi energy represents the chemical potential of the electrons. So this is actually a true statement. Why? Because this is very much representative. When you talk about intrinsic and extrinsic semiconductor, basically the doping of semiconductors with different electrons and different atoms of different periodic table elements. So that is what the semi behaves with as semiconductor because of these doping. So basically the chemical properties are actually changed, and because of the change in chemical properties, the Fermi level actually Fermi energy is also changed. So what are the chemical properties? So this is a true statement. Okay? The Fermi energy level represents the chemical potential of the electron, so it is quite true. The second thing is key you must have wanted to know what are the chemical potential of the electrons, how they are represented, and basically. So chemical potential of a substance is the chemical energy per mole of the substance. Okay, so when we talk about chemical potential of the of any substance, make sure it is the chemical energy per mole of the substance. Okay, so what chemical potential actually represents? It represents the chemical energy per mole of the substance. Electron is so especially in case of electron. It is generally in terms of particle. I have given an example here also. Like basically, is an example of chemical potential. What is the it is the amount of work that is needed for electron to travel in case one volt current is applied. Okay, one volt potential is applied. So that is equal to 1 electron volt, and it's basically represents the chemical potential of the electron. So in case of electron, it is basically per particle, and in case of substance, it is represented per mole, like kilojoule per mole. Okay, kilojoule per more skill when these are precious units. The unit of enthalpy, heat, this unit of specific heat. We talk about different things in chemical potential. From that, what quantum mechanics usually between highest and lowest occupied single particle states in a quantum system of non-interacting fermions at absolute zero temperature. So I will have put the slide also where I will show you different how the electron jump through the insulator, what are the semiconductor. So there we will discuss and have a detailed view about how this Fermi level is actually affected, how the electron jump. So these things are there which will help you gain a particular idea about this Fermi energy level, the various chemical potential and other things. Okay. Here we will discuss about the different valence band, conduction band. We'll see what insulator, conductor, metal, and how these bands actually affect the conduction of electrons from valence band to conduction band. Okay, so I want you guys to take a look at these different type of bands and have a proper understanding how these actually overlap and work. So have a look for 2 minutes and then we will discuss about if there are any questions from your side. Then we will discuss those questions. Otherwise, I will explain these bands to you and how the electrons actually travel from valence band to conduction band, which are insulator, which are conductor, which are metal. Okay. So yeah, we'll talk about this band gap and greater than 2 electron. So yeah, this is valence band, this is conduction band. The electrons from this valence band actually jumps to the conduction band. Okay, if the valence band and conduction band overlaps, electron can move easily. So this is what happens in case of metal. Okay, so in case of metal, actually, this valence band and conduction band overlap. Like we say here, this conduction band and this valence band overlap. So actually, make the metal conducting, very much conducting this. In case of insulator, what happens? The band gap is greater than 2 electron volts. So if band gap is greater than 2 electron from this cannot jump to this conduction band. Okay, it's a very large energy gap that has to be crossed with electron to come to the conduction band. So this happens very rarely. So these are insulators. The electrons cannot move freely here. So this was the main reason that insulators cannot conduct current. But in case of semiconductor, this band gap is actually very less than even 2 electron volt. So what happens if these two are very near to each other, they are doped with extra electrons. So what can happen? Extra electrons can jump to the conduction band. In case of certain circumstances, favorable circumstances, the electrons can move from conduction band to conduction band in case of semiconductors. So these are actually different. Now at 0 Kelvin there must be a energy level here that's called Fermi energy level. So what happens? This is the lowest energy level occupied by an electron. Not the lowest actually, this has the lowest energy, but it's the highest energy level that can be occupied by electron at 0 Kelvin. That is Fermi energy level. So I'm saying that most of you have got a pretty good understanding about these different things. Okay, Fermi level 0 Kelvin. So this is the main thing. Okay, and you can see here, okay, if you see this, and this is actually what happened to each other, which is valence band and conduction band. So this make them a metal. Okay. Now the next question is, the space charge region is always of equal width on either side of the p-n junction. So the first thing is that we need to know what is space charge. So if we got to know the space charge region, then we can learn is equal width from the other side of p-n junction. So p-n junction basically hold carrier depending on different p-doped and n-doped electrode. Here you can see p-doped and this n-doped electrode. So this is the depletion region in which negative goes here and they take charge from here. These actually mix and charge on charge neutrality are found. These are called space charge regions. It's also called depletion region. Okay, so actually in junction there must be some applied voltage, something which actually make it cannot be. So this is actually false. The correct answer is false. And what is base charge region? It's basically a region depletion is from the whole creating a small space of net charge neutrality which I taught here. Okay, you can say if this is speed of the electron, so what it's speed of so negative charge is from there, and if end of the positive charge from here, and these charge actually mix with each other. So what happens? Positive and negative mix, then there is a small stress on that duality form. So there is a electric current also applied. So for movement of the electron, so this depletion region is actually not equal width to the sides. Okay, so depend on the electric field and other components, that voltage depletion region actually varies. And that is how this behaves. Okay, so that these space charge region which are found here are actually static. Okay, and but it contains immobile, that is it contains immobile charge carriers. This is not that this space charge region actually moving it. Next time it is found here or here. This is not the case. It is actually a static, and it's more based at a fixed location found from the mobile charge carriers. Okay. So, so now we move to the next question. I'm sure that this space charge question is really on to, to approach these type of questions. Okay, move to the next question. So the next question actually talks about the direct band gap semiconductors, better suited for solar cell application than direct band gap semiconductor. This is basically algorithm. So for solving this question, you must know what a direct band semiconductor and what an indirect band semiconductor. So actually, I'm saying the direct band semiconductor is actually better suited for solar cell application. So this is actually a true statement. It's true. We'll see in next slide. So actually, what happens when we talk here of semiconductors, like here. So there is a band gap here. We see that there is a band gap here. So this band gap is actually two types. One is direct band gap semiconductor, and second is direct band gap semiconductor. And out of these two types of semiconductor, direct band gaps is basically more suitable for solar applications. So let's see here. Okay, what is an indirect band gap semiconductor? So what happens? Okay, this is the valence band. Okay, so this represents energy versus momentum diagram. Direct band gap semiconductor. So this is basically a valence band, and this is a conduction band. So we see that key. This is the maximum energy level of valence band. Okay, conduction band. So if there is some electron, then it has to travel through intermediate band levels to actually move to the conduction band. So in direct band semiconductor, what happens? The maximum energy of the valence band of different band. energy in the quantity zone, which really kind of uh, inhibits or stops the transfer of electrons. It had to move through different energy levels before going to the conduction. This is actually what I can say is difficult for electrons to move, or they don't have such momentum to move to the conduction band. So that's why direct band gap electrons are preferred. So happens in direct band gap semiconductors. So in that band an electron can shift from highest energy state in the valence band, that is rate, to the lowest energy state, that energy state in the valence band, to the lowest energy state in the conduction band, which is shown through green. Okay, without change in crystal momentum. So these must be so that we can be without any change in much momentum, they can shift to this. So these are very near to each other. Okay, so if this is the momentum without any changing in momentum, that can only change in energy is there. So if I have to give an example for direct band gap semiconductor, say direct band gap semiconductor, so what can be example? So gallium arsenide is an example. So mark this key. Maybe it can ask about different in exam. There can be question that key these are the different semiconductors and so these are that kind of semiconductors. So this is I am giving you examples of different dead band gap semiconductors like night, indium, gallium arsenide, NJAS, cadmium sulfide is there, cadmium selenide is there, CDAC. So these are different semiconductors which are there on that band gap. Okay. So I'm sure you must have got a good understanding about different band gap and direct band gap semiconductors. So now if we let me draw a different, I can show you through example actually direct and indirect band gap semiconductors. So let's say this indirect band gap semiconductor. So if I have to draw the simple energy or some quantum for direct, this is band gap semiconductor. Okay. So let's say this is the conduction band. So this is the minimum conduction band. So it is a valence band. It has the highest at this position. Okay. So this is the highest of valence band. You see that minimum conduction band, the highest of valence band is actually at the same momentum. So this is that band gap semi. But here you see that the lowest or highest of valence band is at this momentum and lowest of conduction band at this momentum. Electron has to pass through intermediate states to reach here within the same moment can reach this energy level. So this is the difference between graphical difference and significance between different and direct and indirect band gaps. Okay. So I'm sure you must have got a good idea about this direct and indirect band gap semiconductor. Yeah. So let me check if there are any questions in the chat box. No questions. Okay. Now we will move towards question 5. Seems like someone wants to join it. Let's check if someone wants to join. So now we will talk about the okay. So metals. Question is metals are usually transparent because of their lack of band gap. So first thing is that the metals are generally not transparent. Okay. Transparent is something through which you can through which light can pass. Okay, so metals are usually opaque. See-through metals. So it's a false statement. The correct answer is false. So if we see the increasing energy and different band gaps, so for metal, these conduction and valence band gap overlaps with each other. But and for insulator, there is a band gap between conduction and valence band gaps, so it's very difficult for electrons to pass. And for this semiconductor, the band gap is very small, so there can be movement from this to this. Okay, so this is the main scenario if we see around different band gaps. So this is what makes them a metals, semiconductor, conductor, semiconductor, and insulator. And metals are usually opaque. So can anyone tell me the reason why metals are usually opaque? So what it why metals are usually opaque. But what can be the reason that metal is usually opaque and not transparent? Actually, what happens, the transparency and opacity of any object actually depends on how the light waves which is coming interacts with the materials. Okay, this is the material. If this is the light wave, how it interacts with the materials of those objects actually called the transparency and opacity. So actually, what happens, the light waves actually cause vibration in the surface atom, which are either absorbed. So either they get absorbed, or they get transmitted, or they get reflected back. So for something to be transparent, there has to be transparency of light wave. And use of metals, what happens? The incident light on the surface is actually absorbed by the large number of free electrons which are present on the surface. So whatever light is coming, the electrons actually absorb the light. So what happens? These electrons has a increase in kinetic energy, and hence because they absorb the light, no light is getting reflected by or transmitted. So that's why metals are usually opaque. Yeah. So you must have got why the metal actually feel like opaque. And some light is actually reflected back also by the metals. So that's why metals appear shiny also. Light is reflected back. Majority of light is actually absorbed, and very less or none of them is actually transmitted. So there is shiny and opaque nature of metals. Okay. So with this, all the graded questions are actually completed. Non-graded question of the assignments are completed.
So I'm sure you must have got a good sense of how to approach those type of questions and different concepts which we have discussed here that we have covered in it. After that, we'll take a break of 5 minutes so that you guys can have a refreshing mood, and then we'll join in 5 minutes so that we'll discuss the graded part of the assignment of previous run of this course. Okay, so if there are anything which you want to discuss or any question you want to ask, you are free to ask in this session. I'm present here. So you take a break also, you think about different questions which I have discussed, and I'm ready to answer your question. So please post your question in the chat box or you can ask me directly till the graded and ungraded part which I discussed till here. Okay. So, okay. So okay. Okay, guys, welcome you back to the session. So you have got no questions to ask. So okay, so I think we should move towards the graded questions now. Graded question of the previous one of the assignment. So let me see if somebody wants to join. Okay, nobody wants to join. Seems like it's a holiday. So most people are actually enjoying the holy celebrations. So yeah, so we'll move towards the materials. Question number 6, which is basically, so we have talked about different graded assignment questions, non-graded assignment questions till now, and after this we will talk about the graded assignment questions. Okay, so and after the ending of this graded assignment question, we will also talk about different concepts regarding the different concepts of the course from weekly lectures. Yeah, will see. Okay, if time permits, we'll discuss that. So if we see this question, it says that can match the following materials with the band gap values. So you must have been sure of this band gap term now. Must have been familiar with this band gap term. And let me see if the recording is actually going on. Yeah, recording is going on. So main thing is that key these videos are actually uploaded on the YouTube also. So for those who have not joined, who had not joined the session, so okay, for this we need to actually show these videos to them. So yeah, I'm saying that key you must have familiar with the term band gap as of now. So if we have to match these materials with band gap, so as we have discussed in the previous slide also here, like 2 electron volt for insulator greater than less than 2 electron volt for semiconductor and for metal overlapping. So we'll use those concepts to solve it. So for metals, it's generally overlapping. So A2 is correct. Insulator is less than 2 electron volt. So B. So sorry. Where is it? Okay. Insulator is greater than 2 electron volt. Semiconductor less than 2 electron volt. So it's A3, A2, B3, and C1. So yeah, it's correct. Now the next thing is that metal is actually partially filled, as we have seen in the previous slide also. So yeah, if it's partially filled, then option 4 is actually also correct. So A4, B3, and C2 are also actually correct. So okay, so both of these, if you are marking, these are correct. So I suggest you guys to have a look and to see answers, and if there are any doubts you want to ask, I'm open to answer all your queries to your satisfaction. Okay, so if there is anything you want to ask me, ask this question or any previous question for which you wanted to ask. Okay, so if there are no questions, should we move to the next slide? Okay, so let's move to the next slide. Now here there is a statement here, and based on the statement, there are three implications out of the statement. So you have to answer which of these are correct based on the statement. Okay, so actually you must have solved these type of questions also in the previous live sessions. So I'm sure that you will you have a good sense of idea how these are to be solved. Oh, okay, so the first is statement is material A has a band gap value of 1.9. Okay, so it's less than 2 electron volts. So what is material A? Material A is semiconductor. So based on the statement, we decided that material A is semiconductor. So the first statement is this material is transparent to the parts of the visual spectrum. Okay. Second is this material is insulating in nature, which is wrong. Cannot be true. Why it's wrong? Because we have decided less than 2 electron volt it's semiconductors. So semiconductor are not insulator; they are conductors. Important type of conductor you can say. Wavelength equivalent to band gap value lies in visible spectrum. So if we have to see visible spectrum, which is 400 to 700 nm, and convert this wavelength to energy, so we see that yeah, this wavelength is actually within the band gap is within the visual spectrum. So this is also a correct option, and this transparent to the parts of visual spectrum. Okay, so the correct answer is both option 1 and 2 are true, and option 1 is true, and option 2 is false. So both, okay, option 1 is true, and both option 1 and 3 are true. C and D are both correct statement. So when you try to solve these type of question, you have to make sure that there are multiple choices questions. Multiple choices means more than one of the choices can be correct. So answering these type of questions can be tricky. So you need to understand that okay, how to answer these questions. So don't just if you select any one question, any one option, and just say that only one is correct. So make sure the other options are wrong. Okay. So multiple correct answers. This this is multiple correct answer question. Okay. So if there are anything you want to ask regarding this question, uh, take a look at this question, and you can ask me questions regarding this. So you have to see. Okay. So let me see if anyone else has joined. Okay, no one has joined. It's already 8:18. So let's complete this session. So we move to the next question now. Now the next question is you just have to match these two with each other. So for matching with each other, you need to actually see the statements, and then if this is true, then match it with true, otherwise false. So yeah, the first statement says that the Fermi energy level lies closer to the valence band in n-type and p-type exchange semiconductor. Yeah, for n-type and p-type semiconductor, the Fermi level lies closer to the conduction band and valence type. I mean n-type, and for p-type, it's closer to valence band. Okay, so this is conduction band, this is valence band. For N-type semiconductor, it will be closer to conduction band. For P-type semiconductor, it will be closer to valence band. So it's conduction band, okay? So this is actually a true statement. Now the second thing is that the band gap of a material can be changed. Yeah, band gap can be changed. How can we change? How can we change the band gap? Can you say or imagine? How can if we have to change a band gap of a material? So how can we change? So band gap is what? A property of a material. Okay. So properties can be changed with different treatments or anything, like if you dope it with some electrodes, or with if you make it alloy or something, we paste it or some. So yeah, it can be changed. So correct answer is true. So one true, one A1 and B1 both are correct here. So I suggest you guys go through it, and if any question is there, I am ready to answer all your queries here. Okay. So yeah, you go through this question. So if there are no questions, then we move to the next question here. Dash band gap material is always preferred over the dash band gap for fabricating. So since there is actually a discussion of fabricating, we have discussed about direct and indirect band gap material. So yeah, this type of question I have also discussed in non-graded assignment type of question. So direct the answer is here. Direct band gap is actually preferred. Why direct band gap is? Because there can be no change in momentum, but still the electrons can move from one energy level balance to conduction. So direct band gap material is actually preferred over indirect band gap material. And for fabricating what? So what are we fabricating? Solar cell actually. Okay, so yeah, the correct answer is answer B, direct, indirect, and solar cell. Yeah, we have actually discussed this question here itself. Here that in that band of semiconductor for okay. So we discussed here. We drew a semiconductor also here. This was conductive mass for this momentum itself. Okay, so that's why this diode band gap semiconductor is actually preferred over and diode band gap semiconductor. So I think this was a pretty much easy question, not of much thinking. So if you guys have gone through like previous question, you must have actually got a good fair sense of idea how to solve this type of question, which can be very easy. So what I do, see this question. If there are any thing you wanted to ask, you can always ask. So yeah, you must have. If there are no questions, can we move to the next question now? So you must have got a good and fair idea of how these conduction and electron bands actually work. So these are very important when you design a solar cell. And for this type of questions, you just need to have a good sense of understanding, clear concept, and you can score good marks in this type of question. Now the next question is conductivity of intrinsics. So, okay, no. So conductivity of semiconductor depends on temperature. Its dash and hence the conductivity can be changed by subsequently doping this material. So charge carrier concentrations are actually common. You need to understand the extrinsic or intrinsic. Okay. So yeah, spelling is wrong. It's intrinsic. Okay. So basically, conductivity of an intrinsic semiconductor depends on the temperature. So this is a correct statement, and its charge carrier can be changed by subsequently doping this material. So first thing you need to understand what is intrinsic semiconductor and what is extrinsic semiconductor. Okay. So basically, if you see, intrinsic semiconductors are those semiconductors. Basically, intrinsic semiconductor are actually undoped semiconductor. They are not doped. Okay. So they are kind of pure semiconductor without any significant doping present. So number of charge is therefore determined by the properties of the material itself and instead of amount of impurities. So if extrinsic semiconductor is there, so its charge carrier not only depends on temperature but also the amount of impurities. But in case of intrinsic semiconductor, it's basically the amount of impurities which it's a property and the temperature determine the conductivity of semiconductor. And also in case of intrinsic semiconductor, the number of excited electrons is equal to number of holes. So these are basically undoped semiconductors. And what are the examples? Silicon, germanium. Okay. So basically, semiconductor in its pure form is intrinsic semiconductor, and when there is a chemical impurity added to the intrinsic semiconductor, the resulting semiconductor is extrinsic semiconductor. Okay, so I think most of you have got a fair sense of idea. So what? Why do we add impurities or something? So basically, impurities modify the electrical properties of the semiconductor, and since it makes it more suitable for usage in electronic devices, transistor, diodes, etc. So that's why we add impurities. So yeah, such things are actually very much covered. It enhances the property also. And for extrinsic semiconductor, it can be p-type and n-type. So in p-type, the hole density much greater than electron density. The receptor energy level of the p-type is actually close to the valence band, away from the conduction band. In n-type semiconductor, uh, the next one doped with phosphorus or antimony as the basic impurity. Okay, so you must go through these type of concepts and have a clear sense of idea what semiconductors are, how, what are charge carrier concentration, what are the different charges that can go through. And what are the doping materials, what are the intrinsic semiconductor, basically examples of intrinsic semiconductor. Okay, so go through this question and I'm sure if there are any doubts, you can ask it in the chat box also because I read the chat box, or else you can ask in the discussion forum also. So those who have not joined this session can have a good idea about the different things and also gain from your questions. Yeah. Also, you can unmute your mic and ask questions. So let me also. So, I'm sure that you must have got a good and fair share. So I will wait for few more minutes to uh, see if there are any questions from your side. Otherwise, I will move to the next question. Okay. Okay, so if there are no questions from your side, so should we move to the next question now? Let me see if there are anyone who wants to join. Okay, no one wants to join. So yeah, so already 8:42. Uh, we have this 5 to 6 questions which we'll discuss, and then we'll move to bring the session. Okay, so let me see the audience. Okay, yeah. Okay. So the next question is basically in a PN junction band bending happen when in a PN junction. So it's talking about PN junction. So what is PN junction? You have heard about the P type and type. There is the depletion region or space charge carrier region. So band bending happens when what is the possible region of band bending? So if you see the possible region of band bending, so it basically because the Fermi energy level varies across the junction is initially formed. Second thing is that the chemical potential of electron on one side of the junction is more than the other side of the junction. So correct option is answer C and D. So this is the main region for band bending in semiconductor. So basically So basically, if we first thing is that you need to understand what is band bending. Okay. So band bending is basically in the space charge region, that is depletion region. The energy band edges in the semiconductor are also shifted continuously. Okay, so energy band are actually shifted continuously due to electric field between the semiconductor and the metal due to charge transfer. So this is what is actually band bending. So basically, why it happens? Why the so actually what happens that key an electric field is developed from the metal to the semiconductor which drives the electrons from the metal. Okay, so first thing is that electric field is actually driving the electrons from the electron. So by moving closer to the metal, the electrons would just lower its potential energy. Okay, and the result is that the semiconductor energy bends downward towards the metal surface. So this is the main reason for band bending. So what we have to do is when the initial Fermi level form, this is basically in case of initial time and Fermi energy level vary across the junction. And the second thing is that chemical molecular what is electricity rather than one junction is more than the other side of the junction. So this is the main two reason for band bending. Okay, so that is the main thing. So please go through this question, and if there are anything you want to ask, I'm here. So basically, you need to understand the concept of band bending here, which is quite an important concept that needs to be seen. So, if there are anything you want to ask, please ask. Okay, so let's move to the next question. If there are no questions from your side. Now here you have to actually match the two profiles. So this is the let's say this is A and this is B. So you have to match section A with section B. So don't confuse these two. Okay. So these are actually same thing: charge density, electric field, and potential. So you know the difference between these things: charge density, electric field, and potential. So potential is something which is like applied to move the electron. Electric field is basically a field created by the movement of electrons or something. And charge is basically a positive charge. Okay. So if you see the level the graph, so basically one is the graph of charge density, so and this is the graph of electric field, and for potential the graph is this. So it's basically a question based on the concept discussed in the weekly lectures. Yeah, only these type of concepts are basically actually you need to see understand the graph of this charge density, electric field, and potential, so that you can easily be able to answer or solve this type of question when it comes in exam. Okay, so I'm sure you you can also have a look at these graphs, how these graphs are actually uh, more sort of discussed for these different type of things. Okay, so I think we have only 10 minutes left and we have three questions to discuss. Okay, so discuss question 13. So yeah, we have to match the different following processes with the column 1 and column 2. So it's basically match the following process. And let me see if the voice is okay. Yeah, okay. So basically we have to match the column A with column B. Okay, so you see column 1 and 2. So it's talking about uh, Sokralski process. Okay, so basically you have to for A Sokralski process it is basically primarily shape limitation due to the surface tension of liquid. So we'll talk about this process later also, but the main is primarily shape limitation due to surface tension of liquid, relatively minimal limitation with respect to size. So the correct answer is this. And for fluid zone process, actually the correct answer is one. Shape and size limitation due to surface tension of liquid. So correct answer is both A2 and B1. And also for Krasky process, the fixed RF heating coils are basically used. So yeah, 3 is also correct. And for fluid zone process, 4 is also correct. Moving RF heating coils. Okay, so we'll discuss about these process also in later slides. I made these slides so that you can have a good set of idea how these processes are actually worked. So as of now, you can take it as it is. Uh, Arrange the following in increasing order of their disorder. So yeah. So if you have to increasing arrange the following in increasing order of their disorder. So disorder you must observe that crystal lattices have disorder. So basically, when we talk of disorder, then the single crystal material have the least disorder. Okay, and then after that we have this small size crystal material, and then amorphous material highly disorder. The particles are arranged in actually much haphazard way in amorphous material. So yeah, the correct is 2, 3. So this is the correct option. Okay. Now the last question, I think. Yeah, this is the last question. So last question is basically ask about name the process which is used to manufacture p-n junction by enabling gaseous element to condense on the surface of substance under high vacuum. Okay, so it is asking about the process which you use to manufacture PNS by enabling gaseous element to condense on the surface of substrate under high vacuum. So high vacuum basically a vacuum process is epitaxy process. On the surface condensation happens. So it's basically epitaxy process. We have Tarski process, diffusion, and float zone process also. So it's basically epitaxy process which it is talking about. So the correct answer is C, epitaxy. So I think we have discussed all of the grade part of the assignment of the previous run of the course. So let's see how much time we have left. So yeah, we have around 5 to 6 minutes. So yeah, we can easily discuss. We have 6 to 7 minutes. Okay, so we can discuss the different processes also. So you can have a good idea. So basically, the first process which I am talking here is basically epitaxy process. So epitaxy is the process of growing a crystal of a particular orientation. So particular orientation on the top of other crystals. So orientation is particular, not haphazard or random. The orientation determined by the underlying crystal. So whatever is underlying actually determines the orientation of the upper crystal. Okay, so what do we have? So we etch and then we put it in ultra vacuum, and there is vapor which actually decomposes on the surface of this underlying metal. So if this is silicon carbide, silicon carbide. So this is actually what happens. This is the actual process. So it's basically vapor deposition on the surface. So it's form a particular orientation. So that's what the question was here. The name process on which by enabling gas element to condense. So what happens? This vapor are actually condensing on the surface. So that is how the epitaxy process actually works. Now, third thing is that this basically is so Kralsky process. I don't know how it is pronounced, so maybe pronouncing it wrong. So yeah, this is the process I think. So it is basically a quartzite converted to metallurgical grade silicon. So this metallurgical grade silicon is converted to electronic grade silicon, and then this is converted to this silicon hydrogen chloride. Okay, so this silicon converted to trichlorosilane, which is purified and reduced back to silicon. So okay, and this is the process. So take a look. First, take a look at this process. So, so what is this? So Pralsky method. So Pralsky process is basically a method of crystal growth, which is used to obtain single crystals of semiconductor like silicon, germanium, or gallium arsenide. So this method is basically not named after a polyscientist, as depicted from the name itself. It's basically a police name, a name of a police scientist who invented it in 1915. So basically, how did he discovered it by accident? Instead of dipping his pen in inkwell, he dipped it in molten steel and travertine filament. So which later proved to be a single silicon crystal. So that is single crystal. So that is how this process was actually discovered. And basically, this is the whole process on which this there is a seed crystal which is rotated and the crystal is grown. They are hitting coils also, and basically the semiconductor grade silicon crucible in our atmosphere is basically needed. So, yeah, melting of polycrystalline silicon, adding of dopants here, introduction of seed crystal. So what happens? This seed crystal growth and completed this how this seed crystal is actually growth into a big crystal. And then there is float zone process. So yeah, we will discuss that also. Please have a look at it. So what happens in float zone process? So it's a technique in crucible free crystal growth method. So what happens is that in float zone, the molten zone is kept into vertical solid rods, as you can see, and by its own surface tension, the single crystal is grown by dipping a seed crystal into one end of the zone and translating the molten zone towards the crystal. Okay, so that's how this growth is actually. So basically, the advantage of float zone technique is that it is a very low impurity concentration in the silicon crystals. So yeah, the crystals are actually very pure. So this is the main thing. Okay, so yeah, and if we actually want to have very pure silicon concentration, then actually this float zone process is actually preferred. Okay. So yeah, thank you. I think all the slides are finished. If there are any queries, you are always welcome to ask me this email ID. Okay. And also these lectures are actually recorded, so they will be uploaded on YouTube also. So you are requested to follow the link which is given in problem solving session. So yeah, those who have not attended this session or want to learn about this, so you can always attend listen it from YouTube. So once again welcome you all to this. Once again thank you for attending this non-conventional energy resources live session 5. So again happy Holi, and we will meet again in the next week with live session 6, discussing about the weekly lectures, questions, graded assignments, various doubts, and other related queries. So I think the time is also almost over. So if there are anything you wanted to ask to me, you are always welcome. Okay. So,